Hi everyone, in this video I'd like to introduce this convolution of two functions. Let me first start with a motivational question. So here's a typical question stated here for Laplace transform problem. We have a linear differential equation with a constant coefficient, and by applying this Laplace transform we can transform that differential equation to this Laplace transform equation. Once you arrive at this stage, typical thing what you do here at this stage is a partial fraction decomposition. So you decompose it into some of more basic terms so that you can easily predict what this y is. So we do here partial fraction decomposition. And as you know, the partial fraction decomposition requires a lot of calculation, especially when you're doing this one by hand. That's a lot of arithmetic and algebra you have to go through. So one naturally may think about the possibility that although this is a linear operator, so we know it behaves nicely with the sums and the constant linear combination over constants, but it's rarely happened that this type of operator behaves nicely with a multiplicative structure. If you think about what happened with the product rule, and that's exactly how difficult things can be. The whole difficulty created by this entire thing is pretty much due to the nature of how the product rule works. For example, with the natural question is that, all right, this can be easily separated into this two part, s squared plus 1 and 2 times s, and times 1 over s plus 2, for example, like this. If these were sum, that's the typical story, that you know which function correspond to this factor in this Laplace transform situation, and you know which factor represent to that. If it's a sum, and you know the answer because of the linearity. But this Laplace transform happened to have this nice property that behaved nicely with this multiplicative structure as well. So in this part in here, so that part in here, let's think about which function under the Laplace transform goes to that. It's absolutely coming from the cosine, so it's a cosine x. That's going to give you s divided by s squared plus 1. Then there's a 2, which is a constant. You can just put it in there. How about this part in here? Because it's 1 over s plus something, and you know it's from e to the negative 2x. That's the basic part. So we know the individual factors are coming from these two functions, and they're multiplied to each other like this. It's a product. And if we want to figure out is there any way we can put these two answers together into an answer in here. If these were again the sum, then the answer is 2 cosine x plus e to the negative 2x. But if it is a product of its two Laplace function, Laplace transform here, you can't just multiply these two. You can easily verify that that doesn't give you this one back. But there is an answer to this one, and that's what we are something called a convolution. This convolution of these two functions goes in there. Right, so rather than me just giving you the answer, then why don't I just motivate a little bit further and how to think about this nice description we're talking about. Of course there's an answer. There's just two functions. There is an answer. And conceptual and abstractly, you can think about there is an answer. But this how simple or familiar this description is the key here. So let's look at the general situation. So let me in general phrase the question like this. We're looking at this usually the right hand side, but here's written in the left hand side, and this portion of the factor of this product of this function and adds, we know which functions and has this Laplace transform. And the second factor, we know which part it is, and if it's multiplied, is there a way to describe y neatly in terms of f and g? So given f and g, we found that by looking at this each factor and what could be this y, so you can phrase it this way and find a nice description of this function y, of course in terms of f and g as general as possible. So what we're going to do is actually we're going to write this as an integral form, and we're going to write that in integral form and multiply and see if we can write it as a Laplace transform of one function. So here, let me write this Laplace transform, product of these two things. So we're going to enter the integral form here and try to rewrite it as a single thing. So this is an integral, so it's 0 to infinity e to the same parameter s. We have to use st, ft, dt. It's a product times 0 to infinity e to the negative. We're about to combine these two integrals. If you have taken Calc 3, you probably have seen this technique before. So we're going to use different parameter, integral parameters, the gu and du. This is just an integral parameter. We're about to combine these two things together, so we have to use different parameter when we put this inside of there. So this is called iterated integral of s and t, t and nu here, excuse me, t and nu, completely independent parameters. So we're about to enter iterated in a so-called iterated integral, or double integral described as an iterated integral. That's what we're about to enter. So if you look at it as a entire thing as a quantity, you can bring that inside. There are a lot of things to you have to be careful about when you do this type of operation, but we're just introducing this method, and before we define what this convolution is about. So since there are two parameters involved, integral variables involved, and I have to be careful. So the well, as soon as we write down order, it's going to be clear. So e to the negative st, and bring that all together inside su, and there's ft and gu all together, and let me write dt, du inside for us in dt. So in this part here is the u value going from 0 to infinity, and outside is a t value going from 0 to infinity. Those are what those values are for. So you can bring that inside and here. This is so-called iterated integral, yet there is no Calc 3. You just do this integral 2 times. But we can interpret this one as so-called a double integral. So here's how it goes. So here's a transition we're making. We'd like to interpret this iterated integral with a double integral. The double integral is integral done over two-dimensional plane. So here we have these two variables u and t. They're varying from 0 to infinity, and t is varying from 0 to infinity. So because of this order, it goes like this: given value of t, anywhere from 0 to infinity, u is varying from 0 to infinity, like that. So there are two variables are varying, and the way u varies is not really limited by whatever the choice of a t is. So double integral actually take this one entirely into one picture. It's kind of one domain, not like two separate lines. So here's how it goes. So here's xy plane usually, but since our variable here is u and v, I'm going to put t here and u there. Maybe I want to do it an opposite way. So u here and t there. So given t, u can be anywhere, right? Between 0 and infinity, but it all greater than 0. So I think all the points of u and t they're covering is this first quadrant. So I'm going to put some dots in there. So rather than putting a lot of shades, like slash symbol here, I just put some dots to indicate that this is the region, right? We're taking double integral over this first quadrant, which is infinite region. So if I call this region D, the double integral of this one can be expressed as this one like this. This is the symbol for the double integral. It's different from this iterated integral. It's a double integral over this region D, which is infinite. And this function is e to the, let me just simplify this using this exponential law, negative s and t plus u. And these two things are general, so you can't do much simplification here. It's ft and gu, and we usually write not du dt, we write a dA, which is representing tiny piece of area here, like a delta x, but here is delta a, not the delta x in the calculus 1 is the short line segment here, this dA, or delta A in the Riemann sum version, representing area of a short piece in this two-dimensional piece in here. So this is a double integral symbol, and if this D region D is the first quadrant infinite region like this, you can convert it into an iterated integral like this. Now, one of the nice thing about this version here, you can see there's some function that it has a two-variable version in it, but at least we pulled out this e to the negative of some variable here. T plus u is a real number, so it looks a lot like right now is a Laplace transform of one function, although there's two variables involved. So I think the key is that we turn this variable t plus u as a new variable v, and then it's going to be e to the negative s times v, and then it looks a lot like a single Laplace transform here, and that's our goal. So see if we can turn this one into a single Laplace transform using this e to the negative sv part. So here is change of variable. We started with two variables u and t, like this in the first quadrant. We're changing this one of this variable t plus u into v and try to rewrite this one. The nature that this domain is a two-dimensional, it cannot disappear. It should be there somewhere. So as we change this v, we got to keep this at least u or t as another free variable, and then we have a two-variable. They're somewhat depending on each other, limiting each other, but still locally we say is a two-dimensional. So that's our v, and see what happens. Now, goal here is that we want to write this one as an integral of e to the negative s times v times some function. So the main variable here is going to be v. So if I write down our goal here, our goal is writing this double integral as an iterated integral of 0 to infinity e to the negative sv. You keep that v in here and dv right there, and whatever this guy is. We want to rewrite this one with this change of variable into this shape. Because there are two iterated integral involved in here, I'm sure there will be some integral is involved in that part. Now, since we want to have this v as an outer variable like this, we're going to treat it like this. Given v value, and t plus u is going to be this v, and we're going to, for example, we have to make a choice. Maybe we're going to write u as in terms of t and v. These are the two main variables, and u is now completely dependent on v and t. So let's write u here. U is v minus t. And as I wrote here, you can see v can be anywhere. T and u are varying freely and earlier. So v can take any value 0 to infinity. You can start from 0. As they vary, it'll reach any large number. So v is totally free. See if it is given v, t can be totally free. For example, if t is increasing from t, it's originally varying from 0 to infinity, given v value, t can't be varying to the infinity this time. You can start from 0, but if t exceeds this given v value, then you can see that becomes a negative. So we can write it in this way. U here is greater than or equal to 0. That's pretty much the only condition that's put on the u variable. Now this one imposes a condition on v and t like this. Greater than or equal to 0. U is v minus t. And v here is relatively fixed while thinking about how t is supposed to be varying. So that makes t absolutely less than v. That's what we talked about here. T cannot exceed v, so that u can remain positive numbers. But t was originally starting from 0, so altogether we have a condition that t is varying between 0 and v. This is one of the aspects of these conditions. We have it here, and you have to really think about all this, if it makes sense, if given a value of v, t varying freely from 0 to v, if that everything makes sense in here. Actually think about it, it actually does, and under this simple transformation. Now let's write this thing down correctly. That double integral, now it becomes, given v value anywhere between 0 and infinity, this part has only v part in it. S is a fixed parameter. Inside part is now variable from t, varying from 0 to v. So let me write down here again. This is supposed to be t from 0 to v, given value of v. The rest of the part is this one here, this f of t, that's the part. And g is now u is v minus t, so it's a v minus t. And inside here dt, and outside there is dv. So if you look at it here, this part is really the function of v here. Given v value, we're integrating this with this dummy variable t. So each time the v varies, this thing varies. So that's a function of v. So we wrote it as a 0 to infinity e to the negative sv, function of v integrated dv. So I really colored this part. If we have two functions f and g, which are one variable function, and what happened to this as we multiply these two Laplace transform of these two functions can be written as a Laplace transform of one function. And what is that function? A nice description of these two functions in terms of two functions f and g is this one variable integral where their main variable involves in this way. So this is called convolution. And because of this formulation, we're going to define convolution of two functions in the following way. So we're going to define convolution this way. The notation, standard notation, is a star notation, f star g. And f and t are function of one variable function. And we're going to create this function to be integral from 0 to x. And this is our main variable, x right there. And t is going to be our dummy variable, f of t, g of that v spot is where the variable goes. So it's going to be x minus t dt. So that's the definition. So I'm going to give you a quick example of this convolution stuff. For example, f of x is e to the x, and g of x is a sine x. For example, like that. The convolution of these two functions in this order is going to be the integral from 0 to x and e to the t. Then f of x changed to e to the t, and instead in here, instead of sine t, we have sine of x minus t and sine of x minus t here with the integral variable dt. So x is changing, x is the main variable. So this is the name of a new function. So for example, if this function, the convolution function, is defined in this way, and what is the value of this function at 1, that means you're plugging x equals 1 everywhere. So 0 to 1, e to the t, sine of this x appears there as well. So it's 1 minus t and dt. So each time you plug in input value, this is how you compute the output value, and that's the meaning of this function. Now here's why, again, summarizing again, why we are considering this so-called convolution is the following. This whole thing it was pretty much shown earlier. If you have two Laplace transform multiplied to each other like this, so that you know this factor, and you can do the inverse Laplace transform of the one factor, and you can do the inverse Laplace transform of another factor easily. We often look at this one, and the standard way to solve this one is usually partial fraction decomposition. But this one shows us another method. It says if you multiply those two things together, go through the double integral and change a variable, we can rearrange to Laplace transform of one function, which is this convolution. This is amazing. You can just detour all the partial fractions composition and just write down some sort of integral description of the problem. So it allows us to write down this answer in a certain way where you don't have to do the partial fraction decomposition. Of course, if you want an explicit non-integral version of a solution, you have to do this integral of this. You have to go through the antiderivative of this function, for example, to unfold this one. You have to do the addition formula and do all that. But it's still, one way or another, it's a very, very nice theoretical description, just like in the variation of a parameter. So in the next part of the video, we'll make a nice analogy with the variation of a parameter, but that does have some cost of doing some antiderivative calculation, but a somewhat much better description than partial fraction decomposition in theoretical way. Now, for example, if you can take this one as an example, and how powerful this, I'm going to show you how powerful this method is. For example, in here, if you're looking for a function whose Laplace transform is the product of the Laplace transform these two, so that is coming from 1 over s minus 1 times that one is coming from 1 over s squared plus 1. So if you're looking at that function, and you have to think about the partial fraction of decomposition, and then we do this one individually. But what this theorem says is that we're going to write this right-hand side as a product of two Laplace transform. This one came from e to the x, that we know, and that one came from sine x right there. So therefore, the y, if you go to the left side, y can be taken as a convolution of these two functions, which is the 0 to the x, and this one changed to e to the t, times this one with the sine of x minus t instead of sine of t and dt. That is the answers in inverse Laplace transform. This one is written as an antiderivative of this function and right here. As you can see in this, the formation and everything, it's concise and beautiful, and then it's a winning idea. In the next part, I'd like to make an analogy with variation of a parameter, and connect this method, convolution method, to in general solving linear differential equation with the constant coefficients.